Yeah, so good morning, everybody. Thanks for coming to my talk about using threaded Python and Julia together. Hopefully, nobody else had to sprint over here like I did from the sponsor talk, so if I sound like a little breathless, that's why. So today I'm going to be talking about some experience I've had trying to write a Python wrapper that itself uses threads and interacts with threaded Julia code, talk about some of the challenges that were encountered, and a workaround that I developed. So I just want to start this off saying that I'm going to be presenting a workaround. I'm not claiming it's like good or even particularly well developed. It's just a suggestion, and also kind of discuss some future prospects for integrating between the two languages that hopefully should make our lives a little bit easier. And I see some other people also just left the sponsor talk, so hello. Okay. So as probably many of us know, if you're a Julia developer, there's quite a bit of demand for Python interfaces on top of Julia code. There's a variety of reasons for this. One is that many end users who aren't sort of like very enthusiastic about developing new packages, or like maybe aren't sort of, we might say like researchers, prefer to stick with what they know, and in many cases that's Python. So probably like a lot of people who've worked in large enterprises, for example, or even other like large institutions, like some national labs, have experience with someone saying like, we've already written all this code in Python, why would we try this new language that like nobody's using, I've never heard of Julia. So if you want your Julia code to get used, it needs a Python wrapper. The other thing, of course, is that once we have a Python wrapper for Julia code, in general, these kind of interfaces make it easy for other third-party Python libraries to call whatever it is we're using. So for example, like if somebody writes a Python wrapper for diffeq.jl, then something like SciPy and all of the other packages that work with SciPy can then integrate with it, and not everybody has to deal with calling Julia successfully themselves. So it opens up the very large world and ecosystem of Python packages, and allows people to kind of try before they buy, where they start out with a small Julia package that's wrapped, and they're like, wow, this is so great. I wonder what else I could do with Julia, and then we've already got them indoctrinated into the cold. So, of course, the other thing that's nice about it, similar to kind of the SciPy example, is that it allows users or people who are dealing with a large mature code base that's already in Python to speed up a hot section of the code, so an area of the code that we're spending a lot of time in, that is called very frequently, like the inner portion of a simulation loop. If you can rewrite that in Julia without having to rewrite the entire Python code base, you can dramatically improve the life of everybody using this thing without having to convince whoever it is to rewrite the entire Python stack in Julia, as tempting as that might be. And on a similar line, of course, everybody knows Python is pretty highly entrenched in what many industries and also scientific domains. I mean, astronomy or biosciences are good examples. And it's not going away anytime soon. I don't mean to say that like I hate Python and I wish all snakes would die or something like that. But Python has a lot of mindshare. There's a lot of tooling available for it, and so whether you like it or love it, it's still going to be around for a long time. So it's worth thinking about how we can effectively integrate our Julia code with the Python code we want to end up interacting with. Okay. But when we're calling Julia from Python, there's definitely some new complications. Of course, this is true in any sort of language A, language B interaction, but we need to worry about how we share objects in memory, especially arrays. One especially important reason for this is that both Julia and Python are garbage collected languages. And so if we're sharing an array back and forth between Python and Julia, we need to be really careful about whose GC owns that array, when did the GCs run for various languages. We better hope that Python doesn't garbage collect an array we're counting on using later in Julia. So we need a careful way to mark things as dirty or fresh and ready to be reused. And we also need to worry about what happens, as we'll see later, when multiple Python threads start trying to call into the same Julia process, how well this works or doesn't work, and also processes like precompilation, which, of course, if you're having to precompile at the start of your Julia process, whatever it is, this usually involves threading. It can involve yielding back into this task scheduler and various other operations. So that's another thing we need to be careful about.
So good morning, everybody.
And Python has its own sort of odd paradigm, if you like, when it comes to threading.
Okay,
so in older Python versions, as we'll discuss, there's this, I don't know if you want to call it like concept or phenomenon, called the global interpreter lock. So for each Python process, only one thread can be executing Python instructions at one time. This is the so-called GIL. And so in effect, Python threads running Python code are sort of like, I guess I was a little uncharitable by calling them fake or they're sort of like lightweight or fictitious, if you like, because only one operation is executing at any one time.
Yeah,
if it's
so good
pure
morning,
Python
everybody.
code, but they can still be really useful for these asynchronous operations. For example, if you have a lot of different I/O operations, you can thread them in Python.
Nobody else
so you
had
can
to
be like
sprint over here
downloading
like I
a
did
file
from
in the
sponsor
background
talks,
while
so if I
another
sound like a
Python
little
thread
breathless,
does something
that's why.
useful while it holds
So
the
today I'm gonna be
GIL.
talking about
Or
some
you can
experience
also
I've had
bypass the
trying to
GIL
write
by
a
calling into a C library
Python
and you wait for it to
wrapper
do
that
something.
itself uses
And
threads
while the
and
C library is
interacts with
executing
Julia
whatever it
code.
is, you've
Talk
moved
about some
on
of
to
the
another
challenges
Python thread that's
that were
acquired the
encountered
GIL and you're
and
like
a
plotting
workaround
something in
that
matplotlib or whatever. But the GIL is something that is, if you're not using Python day to day, is a little bit odd coming from Julia, because of course Julia threads don't have this complication, but it makes calling into Julia code from threaded Python code a little bit complex, as we'll see. The reason this is a problem is, again, as I keep harping on, only one Python thread per process can be executing a Python instruction. So when we want to enter into some other language like Julia's codebase, we have to release or acquire the GIL as appropriate. So we can release the GIL and allow Python to keep doing its own stuff as long as we can guarantee we're not going to be touching any memory that Python owns. So sometimes that's really easy, right? Like if you are writing some library that just passes some simulation parameters, all of which are scalars, into your Julia code, well, that's easy because those guys are all just stack allocated and you can just pass some ints or floats or whatever it may be. And then you can release the GIL and sleep happily because there's no risk that you're going to be touching Python memory. But obviously this becomes a lot more complicated if you have some array that you're passing back and forth. So one technique people use to get around this, as we'll discuss further, is using Python processes, which also is horrible in its own way. Or you can even write Cython, which is for those people who aren't, I don't know if anybody's not familiar with this, but it's a lower level sort of C-like binding for Python, but effectively you have to write this sort of odd hybrid language and call into it and compile a bunch of .pyx objects, which also is kind of horrible. This was a big motivator for the invention of Julia, which kind of tells you like how bad it is. So happily for us, a lot of these complications are managed for us by the wonderful package JuliaCall, which has really nice support for working with Julia threads from Python. There's a nice simple interface for releasing and reacquiring the global interpreter lock. It'll handle initializing Julia for you and install all the packages you need when the Python wrapper module is imported for the first time. Of course, the package dependencies are only installed and precompiled at that first module import for what I'm sure is a very good Python reason that I don't 100% understand. But it's a little frustrating from a user point of view that the first time you install the module, you might be sitting there for 5 minutes waiting for everything to precompile. We can call Julia functions with a suffix that tells Python like, hey, the GIL can be released, go do something else. And that allows us to explicitly flag, like, this code is safe to run without the global interpreter lock, or vice versa, like, nope, I gotta hold on to it when you call into Julia. And again, just to reiterate, this suffix means that you better not be interacting with Python's memory functions at all without relocking the GIL, which you can do from Julia code if you really have to. Okay, so hopefully I've sold you on the fact that it's definitely possible to call into highly performant Julia code, but there's obviously some complications we gotta worry about. And one big one is that JuliaCall is really great. It's a very smartly written package, but of course, like, it can't protect us from every single programmer error, which isn't surprising because I don't know about everybody else, but I'm really good at coming up with new, like, highly creatively stupid errors that I can make. So the ability of human beings to come up with bad code that can work around what the wrapper package is trying to protect you from is basically limitless. And one example of this is if you are using Julia code that yields to the Julia task scheduler to allow tasks to run, you may need to yield from Python to allow the Julia task scheduler to start rescheduling tasks. And if this yield never occurs, then the Julia task scheduler is just sort of sitting there being like, dang, I have this really long queue of tasks. I wish I could schedule some of them. That would be so cool. But I'm waiting for a yield and no one is yielding to me. I'm just still sitting here waiting for a yield. It's a little bit like, I couldn't get a nice picture for this, but if you pull up to a four-way intersection and there's another person across the street and you're like, you go. No, you go. And just no one ever goes anywhere. And so you can inadvertently end up causing the Julia process to effectively enter a deadlock if you can't yield from Python into the Julia task scheduler. And you have to do this occasionally on a repeated basis, and it's kind of an open question on where and how much to do so. But this is a risk that you can hit even at the module import if you're doing something foolish, which I often do. So I've hit this problem where at module import, the entire process locks up, and we'll talk about why. So when third-party libraries like from Python are trying to launch the Julia package wrapper, they can do that in a way that we as Julia programmers can't control at all. So an example of this is that some beautiful Python library that someone has written, I've given it the awesome name, some Python library, creates something called a thread pool executor, which is going to manage Python threaded workers, which use the Julia code. So a thread pool executor is basically like the foreman of the threads, and it tells these threads, okay, when you start up, here's some initial instructions you should run. That's this function initializer, and then you can pass some arguments to that initializer too. So that seems like an obvious place to say like, hey, please yield into the Julia scheduler so that Julia can run all of its tasks. But the problem is, this is some third-party library in Python that's just like kicking off thread pool executors and may not allow us as the end user to say, here's what I want the initializer to be. For example, maybe they have their own large, beautiful initializer that they would prefer to run instead, and there's no way to put ours on the list. Oops, the list of things to run. So it seems like kind of a dead end to ask every single third-party library in Python that uses the thread pool executor to allow us to yield into the Julia scheduler. And this is an issue because this is exactly the kind of behavior that can cause this sort of deadlocking where the Julia task scheduler never gets yielded into. For example, IBM's Qiskit does this. It launches a thread pool executor, and you have no control over how those threads start up. Just as an example, but there's other libraries that do this. And of course, you can go to these folks and say like, hey, please, can you change this behavior? But there's a huge number of Python packages doing this. And ideally, we would protect ourselves so that these third-party Python developers never have to worry about the dumb things that Julia does starting up, or at least the dumb things that Julia programmers have done. Okay. And again, I just want to mention that there are internal functions during startup that can yield into the task scheduler. And this seems to happen just experimentally when I've tried this out more when JuliaCall is not run from a main Python thread. So it's kicked off from like again, a thread pool executor, and one of the worker threads, which is not thread 0, seems to get stuck waiting to yield. I'm not enough of a Python expert to understand why this is, but if anybody here really like knows Python deeply, I would be very interested to hear an answer to the question of why this happens. Seemingly only when the thread number is 1 or greater, but okay. So one workaround to this is to use Python processes to do our parallel programming instead, if we're able to do so. Again, sometimes third-party libraries say like, no, threads only, we don't support the process equivalent of thread pool executor, which is process pool executor. But on our end, as the Julia wrapper library developer, we can use processes to protect ourselves. So just a quick summary of the difference in Python between processes and threads. I know probably you're shocked, like at a JuliaCon, to be getting so much Python content, so sorry for that if that's like a traumatic memory for you. So Python processes, each one has its own GIL. So that means, of course, multiple Python processes can be executing Python instructions in parallel, unlike the threads, where they're subject to the parent process's global interpreter lock. And the other really important difference is that Python threads can share memory objects with one another. All their like arrays live in the same memory space. For processes, that has to be explicitly handled through a bunch of different constructs, like a multiprocessing queue or something like that. So processes, by default, don't share memory with each other. So we have to account for the need to pass arrays, for example, back and forth, or any heap allocated object back and forth between the processes. So again, just really want to reiterate that the risk here isn't just that like we'll have our Julia threads stuck because of the GIL where only one instruction is submitted to Julia at a time, but rather that we can deadlock the entire process as a result of this sort of like task scheduler issue. So the workaround that I ended up using that worked reasonably well for me is effectively to say like on the left here, we've got the initial picture where we have one Python process, which is in blue, and the colors even seem to have shown up, which is astonishing. Then we have some Python threads in green. So these guys are all trying to get some work done, and they're all calling into some Julia process, which is managed by the overall Python process on top. And this is exactly the situation where you can run the risk of the interaction of the GIL and the yield issue locking up both the Julia and Python process, which is kind of inimical to getting any work done. So one possible solution is to say, okay, the Python process is going to launch another worker Python process, not a thread, which will own the Julia process separately. So now these two have two separate GILs, and they'll be able to yield into the Julia scheduler as appropriate, and then we can use some sort of message passing between them to execute instructions from these threads to put onto some like consumer queue for the Julia process. So effectively, this is just some big producer-consumer construction, but by moving the Julia process out into a separate Python process, it allows us to avoid this issue where non-main threads seem to lock up in Python. And this is great because it means that third-party Python developers don't have to do anything. If we execute this correctly, they can just run Julia process wrapper code from like any kind of thread, and it should just work at the cost of having to do something kind of ugly under the hood. There are a bunch of downsides to doing this. One main one is that we have to initialize this process pool for the worker process that owns Julia at the module initialization, which definitely could have some risk of data races. It's hard to share memory with the Julia worker process. We'll see why in a little bit. Also, this is my personal opinion, but the multiprocessing pool interface in Python is not cool. It's not great. I definitely, of course, like I'm a Julia programmer, so I like the Julia channels interface more. And if multiple Python threads want to use the Python wrapper module, then we have to be a little bit careful to avoid creating new processes for each one, and rather allow all the Python threads to share one process. So here is a code sample. Hopefully this is visible in the back of what this kind of looks like. So you can immediately see there's like some big code smell going on here, because there's the infamous keyword global. I feel like anytime you see that in Python module code, it's like a huge red flag if something not good is happening here. So in our wrapper module, we import the pool, and we create some variable to store the pool once we've created it. And then when we set it up, we create one process to manage Julia. We call some function that sets up Julia, like it imports all of our Julia code that we need. And then we make sure that when the parent Python process exits, also the Julia managed process must exit too. So just check and make sure that all of the Julia process work has been finished, and then close it. Otherwise, you'll end up with a dangling zombie process, which is not good. So then setting up Julia, we just make sure that we haven't already imported JuliaCall, and then we set some environment variables that are important to make sure that we don't segfault and that we get decent performance. And then we can just import main from JuliaCall and start importing our Julia packages. Hooray. So this logic would be run on the child process that is managing Julia. And then from this, we can call in and just make sure that we are sending tasks as appropriate to Julia from any of the Python threads. So for example, this logic right here shows how you can do this. I've given it the beautiful name of it runs some task runner. Again, you got the nasty code smell of a global. And this is the sort of syntax in multiprocessing.pool to run something on whatever Julia interface entry point we have. So you just apply whatever arguments you were given to that, and then you also maybe want some logic here, so some function to handle Julia errors so that you can translate them, for example, to the Python error types that Python packages expect, because of course most Python packages like SciPy or whatever it is don't know how to handle a JuliaCall.Julia error. So you may want to translate the error type back to like a value error or a runtime error or something else that Python understands. So this is just sort of a little sketch of how this is all set up. And then the interface runner, which actually does the work, just calls some stuff in my package. And this is, again, running on the child worker process in Python. I've really given some very exciting names to a lot of these functions here. And the other problem that we need to worry about is just sharing memory back and forth. So multiprocessing does allow processes to return arrays from apply, and they can share arrays back and forth. The downside is that by default, this is all done via pickle. Python's pickle is great for some tasks, but it's kind of problematic if the array we have is really large or we're dealing with some custom types that pickle is not sure how to handle. This is, of course, like the infamous problem of serialization and deserialization, which I'm not going to claim to know how to like solve in general here. But the problem with using pickle specifically is that it can introduce really high overhead for the inter-process communication, and this can kill you if you have a large, like 2 to the 20 sized array that you're passing back and forth between the two Python worker processes. So there's a really nice blog post that I have shared the QR for here that you can read if you're interested, benchmarking a variety of different approaches to get around this. One maybe obvious one is like, well, like stop hitting yourself, like stop trying to share giant arrays between these processes. But sometimes the end user wants the giant array, and there's really no way around it. So unfortunately, you can't always just tell people like don't do that, even though it might be the best advice. Another option, which is the one we're going to take, is to memory map large arrays to disk and then load them back and forth from the various Python processes. Obviously, this tends to have some overhead associated with it too, but it's a little more convenient than using Pickle and tends to be faster in real-world benchmarks. And then there's another technique that I won't go into that this blog post discusses called copy on write. And we'll just look very quickly at the mmap situation. So here's a nice example. Hopefully this isn't too verbose. Effectively, we just search through the results of our function, find anybody who's too big, mmap it to disk, and then return to Python the location of the mmapped file and how big it is. Python needs that information to read it back. And then on the parent worker process side, once we get that information, here are the paths, here's how big they are, we can just read back from the mmapped file using NumPy, whatever object it was that we had written to disk. So empirically, this does seem to help substantially with inter-process communication, but of course, the number one thing you can always tell people to do is like just stop trying to copy large arrays. Like, don't do it. It's not good. But sometimes people want to do self-destructive things. For example, giving a talk about calling threaded Python and threaded Julia, so you can't always protect people from themselves. And so if you're looking at this and you're saying, like, Katharine, this is really awful. Like, there's globals everywhere. There's mmaps. I don't like this. It's really bad. I would say I agree. So this is a solution to getting around this problem of your entire process deadlocking because you can't yield into the scheduler because you were called in a funny way. I'm not claiming that the solution is particularly good or that it's like particularly good software development practices, but it did unblock me. So it has that advantage over doing nothing. But if you don't like it, I think that's extremely fair. And I should have warned people to like bring a tomato to throw and be like, this is terrible. How could you do such a thing? But if you would like to come yell at me later, that's fine. I understand. The good news is that the global interpreter lock is going away. So hopefully, no one will ever have to do this horrible thing that I did. So here's, again, a nice QR code linking to this post. It's a PEP about how CPython in 3.13, which is one of the newer Pythons, is going to be supporting what they call free threading, which is like for us just like regular threading. But it means that multiple threads will be able to execute instructions in parallel, which would be great. The problem with it is that a lot of Python packages need to opt into this. They may need to modify their code to support it. So it's awesome that Python is trying this out and they're working really hard to support it. And for really big packages like NumPy and SciPy, like there's a lot of smart people who are working on supporting this. They have also, like everybody's heard of NumPy and SciPy, so if they need to call somebody in to help, they can get help writing thread-safe code that can bypass the GIL, which is great. But of course, we know that the Python library ecosystem is very large. There's a huge number of packages, and a lot of people are using relatively smaller ones that don't have the experience or funding, let's say, to get someone in to help them write thread-safe code. So for now, this issue where the threading paradigms in Python and Julia don't play nicely with one another, partly because of the GIL, is still going to be around for a long time. And unfortunately, we may still be getting like complaints that your Python wrapper code just like completely locks up my entire system. Why? And telling them, well, tell the third-party library to use free threading. Wow. It's probably not going to be a solution for a long time. And the other thing to note is that for now, again, in empirical tests, three-threaded Python tends to have worse performance in some important cases. I can dig up some references on that if you're interested, but it's kind of a problem when we're asking people to do this on our behalf. So again, the short story is that the global interpreter lock, for better or worse, is still going to be with us for a long time. And people like me are still going to be writing horrible workarounds to get around it. So in summary, while the GIL is still present out there in the wild, like haunting us, we need a way to work around it. I presented a solution maybe, that uses a separate Julia controller process to work around this. And you may say, like, well, I think the cure is worse than the disease. I would prefer instead to just tell everyone to use Julia, which is valid. But in the case you can't do that, this is one possible option for getting around this problem. So thanks for your attention. If anybody has any questions, we have like 3 minutes left. So.
So it's not exactly what you were trying to do, perhaps, but have you played with the other direction, having Julia start up first and running your Python process through that entry point, and then is it easier to go in that direction? Then you can set up some communication constructs between Python and Julia and maybe have better control over the GIL?
It's definitely interesting. I haven't tried this myself because the use case I had was someone who, many someones who are like Python users only. They don't want to hear about Julia. They don't want to know about it exists. So I needed some way for them to have an experience that like seemed like pure Python, but secretly like under the scales, if you like, it was Julia. And that's like kind of where all of these frustrations come from is, you have some end user who's using some Python library that's doing something wild with thread pool executor, and you can't control what this third-party library is doing. So like, how do you protect the users from having bad performance? Or even worse than bad performance, like their whole system just like sitting there at 100% CPU doing nothing.
So like with packages like BAT, where you have Bayesian sampling, and I may want to support some Python package like ultranest for nested sampling. Currently, I do this with PythonCall, and it used to work with multi-threaded target evaluation in Julia. Now I just tell people you have to go to one thread. Now I want to switch to PythonCall, but it is now Julia basically calling into Python, calling back into Julia. And maybe within one process, and even worse, if people then want to use BAT from Python, they will have Python calling BAT with the sampling algorithm, which will call Python around the wrapper, which will then call back into Julia, which will then call the wrap Python target function. Is this at all feasible?
Probably not, which is again why I say this is like not necessarily the best solution. It's really targeted for my weird use case.
No, I mean with the lock and unlock GIL macros and so on.
Oh yeah, so that I think is feasible, but then you have to be very careful because you're now like on this downward spiral of like who owns the GIL. And it's hard to reason about. And of course, it's sort of similar to the M mapping question, right? You can tell people like, well, just don't call back into Python, but like people love doing silly things. I mean, I love doing silly things, obviously. So yeah, I don't know if I have a good answer for you.
Can we get our next speaker setting up? And we have time for one more question while that happens. Or not. Yeah, let's give the speaker another round of applause.